Okay, planar graphs. What do we mean by planar graph? We will study the question whether a graph can be drawn in a plane without edges crossing. يعني حتى so that I make the idea clear before we go to the definition. Look at the this cubed, which is Q3. This is a kind of graphs. The 3 cubed we call it here, or the n cube if we replace 3 with n. Okay, now can we transform the graph at the left in here? It is in 3-dimensional graph. Okay, and if we look at these intersections here, they are not intersections, so the edges here are not intersecting because this is in 3 dimensions. So that edge behind is far from the edge in the front, so they are not crossing. So the question, can we transform the graph of Q3 to a graph in the plane with no imagination of a 3 dimension? Can we transform it to equation in the plane so that the edges do not cross? So this is the question. If we can do this for a graph, then we will call it a planar graph. So a graph is called a planar graph if it can be drawn in a plane without any edges crossing. Such a drawing is called a planar representation of the graph. So now if you notice, the graph here is the same as the graph of Q3 at the left. They are the same. It's a matter of deformation. If you take the square from inside, pull it outside and make it bigger, then you get back to the Q3 to the cube at the left. So we could draw it in a plane without crossing edges, and same thing for that one. Just take one of the edges and just make it go around. So each of these 2 graphs are planar graph. So this is the idea of this section. This is the concept. Given a graph, can we draw it in a plane without having the edges intersecting, or any intersection of any 2 edges? This is the question. If we can do it, then we will say the graph is a planar. Planar means we can draw it in a plane. If we cannot, then it is not a planar. Okay, and here's a graph of not a planar graph, which is K33. Do you remember what that means? K, M, N. This is a bipartite graph from M vertices to N vertices, and it is complete bipartite graph, which means any vertex in this set must be connected to every vertex in the other set. Okay, now can we draw this graph here in a plane without having edges crossing? And the answer is not. We will not be able to do it. So let's play with it and see why we cannot do that. So first thing, working with this edge here, V1 to V2, okay, and V1 to V5, sorry, V2 to V1. Okay, so we have these 4 vertices and the edges crossing between them. Flip this, so we end up with okay, so I will also take the edges connecting V1 and V4, V1 and V5. So I got this crossing with 2 edges at the side. Flip it this way, then we get a square. So it is in red here. Okay. Okay. Now, so we demonstrated V1, V5, V2, and V4. So we need to add to this V3 and V6 and connect them correspondingly. Now we shall put V3 somewhere. Now in here what it does, it puts V3 in the middle. Okay, it says okay, V3 is connected to V4 and it is connected to V5. So let's go and connect it. This is to V4, and to this is to V5. Okay. Now where we shall put V6? Let's try it. If we add V6 to be here, okay, we notice that V6 is connected to V3, right? So we have to draw this line. And if we do it, we will find ourselves crossing an edge between V2 and V5. So we cannot do that. So we cannot draw V6 outside the square. So where else shall we think to draw V6? Maybe inside the square, right? So where? So let's say it comes here, V6. Then V6 is connected to V1. Okay. And we can do it, V1 to V6 to V1, and V6 is connected to V3. Okay. And it is also connected to V2. So it has to go somewhere here, and this is a crossing, so we could not do it. So what else? We put V6 here maybe? We will have the same problem because we have to connect it to V1. So we have no choice. We don't know where to put. There is no place where we plot V, and so R equals E minus 2, 30 minus V, which is a 20, that's 10 plus 2, so we have 12 edges. So we have 12 edges. I just noticed there was a window in the other screen that it was blocking the recording, so I hope that window has not been there for long, because if it was been there for long, so it was blocking the center of the recording. Okay. Okay, now this corollary will tell us something. Let's see what it says. If we have G connected planar and simple, so it is connected planar and simple graph. Three things. Number of edges is E. Number of vertices is V, but it has to be greater than or equal to 3. Then the number of edges must be less than this formula. Number of edges less than 3 times the number of vertices minus 6. Now how this corollary will help us? It says if the graph is a planar, then this must happen, right? And remember, P gives Q. This is equivalent for saying not Q gives not P. Okay, so what we get here, if E is greater than 3V minus 6, then we will conclude that G is not planar. Good. So we are assuming we have a connected simple graph, and the issue here is the planar property. So if we find the number of edges greater than 3V minus 6, then that graph is not planar. We don't have to keep playing with it. For instance, K5 is non-planar. What is K5? It is the complete graph that has 5 vertices. What do we mean by complete graph? A complete graph is the graph for which every vertex is adjacent to any other vertex in the graph, which means all vertices are connected to each other. So to recall that, so we have K5, that means we have 5 vertices, 1, 2, 3, 4, 5. So every one of them is connected to the other. So this is connected to every one of these in there, and this connected to every one of these, and this connected to every one, and disconnected. Okay, so every other vertex is connected to the other. Every vertex is connected to every other vertex. Now, is this a planar graph? Shall we play with it? And the corollary say no, don't play with it. To compute the number of edges. So what are the number of edges for K5? Shall we count them? If we do so, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that true? 4 plus 3 plus 2 plus 1. Did I miscount? They are 10 or 9? I get 4 plus 3 plus 2 plus 1. That's 10, right? Because the first vertex connected to every other one, that means I have 4 edges. And then the second vertex is connected to every one, then that means I have 3 edges. Then this connected to 2 more, then I have 2 edges. Then I have 1 edge in here. So how many we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the number of edges for K5 is 10. So these are the number of edges, is 10. The number of vertices is 5. So let us see. 3v minus 6 equals 15 minus 6, which is 9. And this is 10. This is E. It equals 10. And it is bigger than this. Okay, so we got this. We got that thing. So K5 is non-planar. So this helps us sometimes to decide that some given graphs are not planar. But it does not give a full characterization. Okay? Does not give a full characterization for which primes are planar and which are not. Okay. Let's see another corollary says if G is connected planar symbolic graph, then G has a vertex of degree not exceeding 5. So again, if it is connected planar symbol, then has a degree not exceeding 5, has a vertex. So that means there exists a vertex, and the vertex set V with the degree of that vertex not exceeding 5, which means is it less than or equal 5. So one vertex is enough. Therefore, if we have a graph whose degrees every vertex in there has a degree greater than 5, that means we have no vertex with degree less than or equal 5. Then the graph is non-planar. I mean, we are using here the contrapositive. So let me rewrite the corollary. It says G planar. So it is connected and simple. Then that means there exists V such that degree of V is less than or equal 5. Okay. Now the contrapositive is here there exists V whose degree is less than or equal 5. The contrapositive of that, for every V in the set, we have that I can write it this way: degree of V is greater than 5. This is the negation, and this gives back the negation of this. G is non-planar. Okay. And there's an example in case 7. What is the degree of an element in K7? K7 is a complete graph with 7 vertices, where every vertex is connected to any other vertex. So we have 7 vertices. Pick a vertex in here. then that vertex must be connected to every other vertex. But we have 6 vertices left, and this is number 7. So every vertex will be connected to 6 vertices. That means the degree of every vertex is 6 exactly. So in here, if V belongs to the vertex set on K7, then the degree of V equals 6, which is greater than 5. So for every V belongs to V, we have degree of V greater than 5. So by the above corollary, K7 is non-planar. Okay, so we have 2 corollaries that help us to decide whether a graph is planar or no. And let's see what we have more. Okay, so one more corollary here. It says connected planar simple graph with number of edges E and vertices V more than 2 vertices, 3 or more. So connected planar and simple, and no circuit of length 3. No circuit of length 3. Then the number of edges must be less than 2 times V minus 4. So connected planar and simple, and there is no circuit of length 3. Okay, so how that will help us to decide some graphs are non-planar. So we will do the contrapositive, and the contrapositive says if I have E greater than 2V, but in what graph we are working here, let me see, then G is non-planar. But I cannot apply this to any graph. It has to be connected, simple, and it has no circuit of length 3. Okay, no circuit of length 3. Then if this happen, we will conclude J is not planar. But we must have no circuit of length 3 to benefit out of that corollary. So let's go to K33 again. We proved it is non-planar, but here we will get a direct proof using the corollary. Now, does the graph K33 satisfy these 3 conditions? It is connected, sure. It is simple, yes. And it has no circuit of length 3. Let's try. Can we do a circuit of length 3? Like if I go from here to here and go from here to here, if I want to have a circuit now, I'm not allowed to move anymore. I must go back to V1. So I must go back to V1. I cannot do so because I have no edges here. So I failed to make 3 by 3 vertex circuit, sorry. So shall I try again? Okay. You know, we have V1, V2, V3, V4, V5, V6. So if we want to do a circuit of length 3, we go from the vertices above, and then we will come back from above to below, then we come back to above. Then to close the circuit, we must go back to V1. But you see the vertices up there are not connected. There are no edges between any 2 vertices up there or down here. So we cannot do a circuit of length 3. Now, this graph has no circuit of length 3, and number of edges, how many edges we have? 1, 2, 3, 4, 5, 9. This is the number of edges. And what's about 2v minus 4? It equals, we have 6 vertices times 2, that's a 12, minus 4, 8. And okay, so this happened. So K33 is non-planar according to the above corollary. So graph coloring. The idea here is how to color the regions drawn in a plane so that no two regions have the same color. Sorry, no two adjacent regions have to have the same color. Okay, so if we want to play with that, let's say, okay, let's give this blue. Let me give this red. Then I cannot give C neither blue or red, green. Sorry. So I will give it red. Okay. So I cannot color D blue because it is adjacent to B, and B is blue. I cannot color it green because it is adjacent to C, and I cannot color it red too. So I will go choose purple. Okay. Now I can color E to be blue E because it is not adjacent to B. Now, this is fun, huh? And I can color F to be green and color G to be red. So how many colors I needed? 4 colors, huh? Interesting. So what's about this one? Do I need 4 colors or less or more? More. Okay. So if you go this way, then I can go, okay, this is green. I can see it. Okay. Oh, so this is easier. So this is a blue. Okay, no, this is not blue. So this is blue now, and this is blue. So I needed only 3 colors for this graph. Okay, but I needed 4 colors for this graph. Okay, so this is the idea. How many colors I need to graph? How many colors I need to make colors for a map so that no two regions, adjacent regions, have the same color. We can transform this to graph theory. Okay, how we do it? We will use vertices to denote the areas. So for this area B, we used a vertex B, and this is vertex A. Now, because B is adjacent to A in this graph here, then we connected them with an edge, and now B is adjacent to A. And also B is adjacent to C, then we connected this way, and C is adjacent to A, and also C is adjacent to D, and D is adjacent to both A and B. So we transformed the map, this map here, to a graph with vertices and edges, where vertices represents regions, and two vertices are adjacent, connected by some edge, if the regions they represent are adjacent regions. So we can transform every map to a graph. And then the question becomes, let me erase that now because we want to preserve colors for vertices. We were asking if we can color the regions, and now regions are represented by vertices. So the question will be whether if we can color the vertices on the graph so that no two adjacent vertices take the same color. So again, the problem is how to color all the vertices in the graph so that no two adjacent vertices take the same color. And this problem is very important in graph theory, and in general it is not easy to answer. But for some simple graph, some special kind of graphs, we can make answer for this. Okay, so transforming a map regions to graph, the resulting graph will be called the dual graph of the map. The dual graph of the map. Now each map in the plane can be represented by a graph in the way I explained. Each region is represented by a vertex, and edges connect to vertices if the regions have common border, if they are adjacent. And then, as I said, the problem of coloring regions of a map is transformed to the problem of coloring vertices so that no two adjacent vertices have the same color. So that motivates for the following definitions. As we asked before, what is the number of colors that we needed to do such coloring? And this will take a very important definition in graph theory in general. And here we go, the definition. What we mean by coloring a simple graph? Simply, it is assignment of colors to each vertex of the graph so that no two adjacent vertices have the same color. All this thing, we call it coloring of the graph. So if we are given a graph and then we are asked, can you color this graph? Then that means giving colors to vertices so that no two adjacent vertices have the same color. So that means coloring the graph. So it is not a random coloring. It's coloring according to that condition. And now the question becomes here, what is the minimum number of colors that I need to graph, to color a graph, for a specific graph? Above there we have seen when a graph needed 4 colors. Let's go back to them. And the other graph needed 3 colors. So let's go back to them and have fun coloring these vertices. So we give blue for this vertex and this vertex, and we give red for G and for A, and we give green for C and for E, and we gave purple for D. Okay? What about the other graph? We gave red for C, green for B, another green for D, and blue for A and C. Now we can see easily here no two adjacent vertices have the same color. But in here we needed 3 colors only. In here 3 colors were not enough. We needed 4 colors. So the question is, given a graph, we want to color that graph. What is the minimum number of colors that we need to do such a coloring? This answer depends on the graph itself, okay? For some graphs, 2 colors are enough. For other graphs, 3 are enough. For some other graphs, we need 4. And interestingly, there is a theorem that says 4 at most. So there is no planar graph, planar, not necessarily planar, there is no simple graph that needs more than 4 colors. 4 are enough. How do we know that? This is interesting. We will see it. We will see the story about it. Okay, now we talked about the number of colors. That number has a very famous name. It is called chromatic number, and it is denoted this way. So a chromatic number of a graph is the minimum, the least number of colors needed to color that graph. Again, the chromatic number of a graph chi of G, this is read chi of G, is the least number of colors needed to color the given graph. And in general, it is difficult to find out this number for any for graphs in general. And this is still a big challenge, a problem for many kind of graphs. People still don't know what is the number of colors needed. And if we talk about planar graphs, this will be kind of less difficult, but other non-planar graphs, the problem will be much difficult, and it is still challenging. Now let's see examples for chromatic number 4 graph G in here. So let's play with coloring. It says the chromatic number is 3, that means 3 colors are enough. So let me play. If I color this red, then I have to color E in different color than red, and A because they are adjacent to B. Sorry, okay, and A. Can I color? Okay, can I color A with blue? Yes, because it is not adjacent to E. I already gave a blue for E, but I cannot color D with blue. So I cannot color D with red because it is adjacent to blue and red. I will give it green. Okay. Now let us look here for C. Can I color C red? No, because it is adjacent to B, and I cannot color it blue because it is adjacent to A, and neither green. So I will have to choose to go for one more color, okay, which is purple. Now I can give this red, okay, and same reason I have to go for purple on this. So I could not use the 3 colors, at least because, you know why? Because of this part of the graph. Okay, so what about this graph now? Okay, 4 colors. No, it says sorry, forgive me. It says that we can do it in 3 colors, but I was not lucky choosing. I was planning for 4 colors in my mind. I was not lucky choosing playing with the vertices, and nobody corrected me.
Doctor, you should put A and D the same color.
Yes, so lead me please. A and what?
D.
A and
D.
D. Yes, please keep going. Help me more. Okay, and can we go for G also? Same color? Now, if we do this color here, that's fine. Okay, good. So now we have 3 colors. I have in mind it is 4, so I wanted to make it 4. So 3 colors were enough. But now we cannot do coloring this graph in here, H, the graph H, with 3 coloring, right? So it has to be 4 coloring. So if we go for this for red, we can go red again here, but I cannot go red for G because now it is connected to A. So I will choose blue for G. So let me choose purple for G. Okay, now I have for E, I must choose something different than red and purple because it's connected to red and purple. And okay, we can go here blue, but we cannot go blue here, so we go, okay. So in F, I cannot go red, cannot go blue, cannot go purple, so I will go for green. So 4 colors. So chromatic number here is 4. Okay, now the 4 color theorem. This is now an interesting theorem. It says that if we have planar graph, a graph that we can draw in a plane with no edge crossing. It says the chromatic number for a planar graph is less than or equal 4. This theorem tells you that if we have a graph which is planar, then 4 colors are enough, and maybe less, to color the graph. This is interesting theorem. It was conjectured in the 1850s and was finally proved 126 years after that. And there were many trials to prove this theorem, but there were mistakes that were very hard to discover. Please read from the book the story about the proof of this theorem. Even this theorem here, it says part of the proof here was based on computer computations, and people don't trust computer computation as proofs. They are useful, but maybe not for proofs, because some bug might be on the application or the software used to do these computations. So people are still with some doubt about the proof of this theorem, but so far all known graphs, planar graphs, needs 4 or less number of colors to color them. So the chromatic number of such graphs is less than or equal 4. Very interesting theorem. Okay. Okay, now it says if the graph is a planar, so let me rewrite this. If the graph is a planar graph, GE is a planar, then the chromatic number is less than or equal 4. Now the contrapositive of that says if we find that for a given graph the chromatic number is greater than 4, then the graph in hand was non-planar. Fine? Okay. Now the chromatic number of Kn is n. Here we go. Okay. So the chromatic number, if n has more than 5, if Kn, or if the value of n is 5 or more, so we mean if we are talking about now here K5, K6, K7, and so on. Remember, these represent complete graph of n vertices, and every vertex is adjacent to every other vertex in the graph, and therefore we cannot color them. There is no way to color them with less than 5 colors. For instance, to make these things clear, let's see to this side here. Let me draw K5. K5 is a color with 5 vertices. Is a graph with 5 vertices. Now every vertex is connected to any other vertex. Now let's try to do coloring for this graph. Now if you choose, for instance, blue for this one, you cannot choose blue for any other vertex, because this blue vertex is connected to every other one. So to color the other vertex, we will use different color, red. And also we cannot choose red for any of the remaining vertices, because each one of them is connected to the red one. So if we want to keep going in coloring, we have to choose different color for every vertex. Okay, so we need 5 colors, the same number as the vertices. And same thing applies for K6. We need 6 colors. For K7 we need 7 colors, and for Kn we need n colors. Therefore the chromatic number of Kn is greater than 4 whenever n is greater than or equal 5, and that will make us conclude that Kn is not planar according to the theorem. Okay, let me get some space here. That will make us conclude that Kn is non-planar where n is greater than or equal 5. Okay? Okay, what is the chromatic number of Kmn? What do we mean by Kmn? This graph, it means we have m vertices in here and n vertices in here. Say for instance I'm drawing here K5, 3, and now every vertex here is connected to every vertex in the set in the top is connected to every vertex in the set in the bottom here, but no vertices in the top, no two vertices in the set in the top are adjacent, and no two vertices in the set in the bottom are adjacent. So how many colors we need? Apparently 2 colors are enough. We can give the vertices in the top there the same colors because no 2 of them are adjacent, and the vertices down here we can give them also the same color for the same reason. So 2 colors are enough. So this graph is not planar, but 2 colors are enough. Okay, what is the chromatic number of Cn? Remember, Cn is a circle within vertices. Okay, and that's worth some discussion, and let's find out this by doing 2 examples. Let's take C6, which means we have 6 vertices. Okay, so these are 6 vertices. Let's try to color them, and they are connected this way only. This is a circle, remember? Okay, so if we give this color red, so okay, we will go for this for blue. Okay, we can go back for red again for blue. Yes, go to blue, and then for red, and one more time for blue, and then this will be blue now. Yes, okay, so we're done. 2 colors were enough for C6. Okay, let's see what happened with C5. Are 2 colors enough again? And this is not G. C5, circle with 5 vertices, and they are connected this way. Okay, so let's play the same thing. Red, blue, red again, blue. Okay, now can I go for red for the remaining one? I cannot, because it is adjacent to the first vertex in there. And I cannot go for blue. So I am forced to use 1/3, one more color. And therefore now we can generalize this by saying if we have n to be even, then there will be one vertex after another, and then when we come back to the last vertex, we will find like it is one of the others. the other colors. So 2 colors are enough when n is even. I think these 2 examples uncover the idea for you. When n is odd, we need 3 colors. Okay? And actually, if you look at this graph in here, where n is even, it is a bipartite graph, which means that I can split the vertices into 2 sets, so that the edges of the graph are edges from one set of the vertices to the other set. So I can take the blue to one side and the red to the other side, and then I get a circle, the C6.